All right. Hello, welcome everybody. Thank you for attending today's webcast. This is Modeling Domestic Hot Water Systems to Understand Energy Use. Sorry, we're getting started a little bit late here. I am Chris Perry from ACEE. I will be helping moderate this session. So we're going to start this webcast with a few housekeeping announcements. I'm sure a lot of you have heard these so far, but we'll go through them again. Then we'll move on to our speakers and followed by Q&A. So to remind you all, your screen is customizable. You can use the various widgets found in the bottom of your screen. The presentations can be downloaded as PDFs from the resource list in the menu. Attendees are in listen-only mode, but you can submit questions through the Q&A box at any time during the webcast. Presenters will be answering questions following the presentation. All the presentations will be available for on-demand viewing within a few days on the Engagement Hub. Zoom discussion rooms will be open at the end of the webcast and continue the conversations and allow for additional questions. So you can click on the Zoom widget or download the daily Zoom link PDF on the Engagement Hub. Please be sure to complete the forum survey after your last webcast. It helps us in planning for future forums and next year when we're in person, hopefully. And last, we want to thank our sponsors and partners for their support of the Hot Water Forum. And so right now I'd like to introduce our distinguished panel of speakers. And I'm going to go in order here. So first is Jim Lutz. He's an independent researcher and a professional engineer based out of California. And Jim is an ASHRAE member on Technical Committee 6.6 of Risk Water Heating. I'm the chair of Standards Project Committee 118.2, Methods of Testing and Rating Residential Water Heaters. And he's been in the industry a long time, a major contributor on our Hot Water Forum Steering Committee. Next speaker is Carmen Cejudo, is a PE building engineer and water efficiency research engineer at Pacific Northwest National Lab, or Pnnl. She selects and develops technical approaches to complex research challenges by leveraging a deep technical background in building science. And our final presenter is Miriam Blocker. She's a principal scientist at the Drinking Water Infrastructure team. She's an expert in drinking water demand and developed the Simdium model, which can be used to predict water demand for toilets, showers, toilet flushing consumption, et cetera. And she uses her model and research on the impact of flow speeds and residence times on water quality in the pipeline network. She completed her PhD on the subject in 2010. And so I'm going to turn it over to our first speaker, who I believe is Jim Lutz. And I know we have another moderator, Sean Orm, who may be coming in to fill in. So if he's able to join, he will be moderating the Q&A. But now I am going to turn this over to Jim.
Hey, Chris, thank you. Hopefully you can see me and hear me and everything's good at my end. And I get to control the slides now. So I'm just going to start off with how to think about modeling domestic hot water systems. This is just sort of conceptual, but it's a conceptual talk, but I'm trying to get across what we can do, what's involved. And so what can we use simulation for? Energy consumption, as the title of the session is saying. It can also be used for design work, the pipe and equipment sizing and the impacts of plumbing layout. One that we've heard a bit about in the Hot Water Forum before is safety, trying to figure out what pathogens might be growing in the water. There's from the water utility side, there's a term called water age, which is how old the water is since it left the treatment plant. And that's something that you can understand through simulation. And then there's another one that I've been starting to hammer on or bring up a bit more is the quality of service and performance. You've all probably heard or experienced the question of you turn on your hot water tap and it takes 30 seconds to get hot water. That, if you can come up with a simulation model that does that or predicts that, then it'll help you with design and how well you're providing hot water service. So the next slide is, what is a domestic hot water system? This is a cartoon I've used for several years now. And I want to start with people, because there's no hot water use in buildings without people. I suppose there's a few cases where it is automated, greenhouses or something. The people decide what fixtures or appliances to use when. Those some use hot water, since this is a hot water form. Some of them also use energy, like dishwashers. Some of them also use cold water, like showers and sinks and faucets. You've got a hot water system, delivers hot water to the fixtures. Some systems are large enough. You have a recirc loop, and then of course you have the water heater, and on some systems you have drain water heat recovery. So I'm going to step through each of these sections and just describe briefly what might be important to consider in some aspects. As I said, there's no hot water use without people. In residential use, it's primarily showers and faucets. Dishwashers, clothes washers, especially the more recent ones that are built under recent efficiency standards, use surprisingly little. And baths, an individual bath uses a lot, but there's surprisingly few baths in the field data. That's not the same pattern in, say, a restaurant or a gym or some other building type that uses hot water. It's very stochastic. It's short pulses. There's general patterns of when they're available. It depends greatly on the type of people, how old they are, what they do. It's sort of, are there teenagers in the house or just old folks with gray beards like me? There's also an interesting thing that I don't think very many people in the hot water forum have thought about, but there's behavior, what people actually do, and then their motivation. Why do they do that behavior? And that's, things like showering has, over the past 3 decades, has become predominant. Prior to that, people bathed. The number of showers, the number of baths per week have changed a lot over the years. And the other thing to pay attention about people is that's important for designing systems and sizing systems is how often are hot water draws happening at the same time. The old Hunter curve, which unfortunately still a lot of the sizing codes are based on, was developed back in the 1930s. There's a new hot water demand calculator based on much more recent field data out of IAPMO, which should probably be used for sizing systems now. That's based on residential data. Fixtures and appliances, those have some level of human interaction. Some of them, like a shower, obviously the person turns it on, controls it. Others are, you set it up and push a button, and then when it's ready, it draws hot water, like a dishwasher or a clothes washer. There's existing standards for most fixtures and appliances. Those standards are likely to keep reducing water use. I want to point out, though, that the standards have not always been successful at reducing water use. And shower heads are a good example of this. If you look at this chart, which hopefully you can see better than I can see, you'll see that toilets and clothes washers, the water use between 1997 and 2016, there was a significant drop in water use, hot water or water use. And that was due to the standards. So that's the impact of standards. The third set of bars from the left is showers. And you'll see there's hardly any drop in water use. And that's after the low flow shower heads standards went into effect. So low flow shower head standards were not a success. And someday I can bend your ear about what I think that was. Reasoning for that. You also have to be aware of regional differences on appliances. The US, we plumb dishwashers to hot water only. In Europe, it's to cold water only. So you have to keep thinking about that. The plumbing, this is the part where the hot water is delivered to the fixtures and appliances. During a hot water draw, there's 4 phases: a startup, a steady state when it's being used, think of a shower, a decay when it's done and the temperature in the pipes is cooling off, and stagnant, where the temperature of the water in the pipes is room temperature and nothing is happening. That pie chart is my guess at the amount of time that the water in the hot water pipes is in the various phases. By far the most common phase is stagnant, nothing's happening. And the steady state is surprisingly uncommon too. Mostly it's startup and then decay. The fittings are the connections in the pipe. They're supposed to be minor losses if you look at the pipe sizing in codes, but they're actually probably much larger than minor. It depends on the flow rate, will give you the pressure drop through that fitting, and that determines the pressure at the end use, like the shower head. So are you getting enough showered? There is surprisingly no standard test procedure developed to rate the flows through fittings under different pressures. Gary Klein's been doing a lot of work on that. And then the water age is primarily most important, I think, in the plumbing. There's biofilms. There's always biofilms on the inside of pipes. You know, hot water forum, I found that out. And not sure I like it, but it's always there. Some of them are pathogens. And we maybe don't want to keep the water in the pipes hot, because that's where the pathogens grow. The recirculation loop is only in larger systems. The plumbing system that I was talking about on the previous slide is a tree. There is a hot water source and an end use, and there may be branches off that tree in different segments, but it's always a tree. The recirculation loop is a loop. They're usually only on larger systems, central systems. It's mostly steady state flow. Although there are some that are on demand, it's usually oversized and too spread out from an actual performance point of view. If it's not insulated, it'll be a major heat loss in the system, and that's hard. It's an important thing to look at. And then there's a new issue coming up that I've just learned about, is the branch off to the right in the diagram here is off to your shower or sink or wherever. When that's stagnant, it's going to cool down to room temperature. And if your central pipe, the vertical one here, is on your recirc system, that's always hot. So that means and it's hopefully hot enough that none of the pathogens in it are growing. And the branch pipe off has cooled down, so there's no pathogens growing in it because they don't grow at room temperature. But there's this transition region where it may be an incubation zone for Legionella every time there's something coming off of Recirc Loop. I think I'm past my time, but I'll try to speed through. Lots of different types of water heaters. There's good standards. There's good test procedures for those. There's certified directories of certified products. Simulation models are available, but there's no standard to verify a simulation model and say whether it's good or not, whether you should use it in your simulation model of the whole building. Drain water heat recovery, that's off of a shower. There's warm water going down the drain. You can use that to heat up the water, the hot water, for either going to the water heater or going to a shower. There are modeling algorithms for it. They obviously work best when you have continuous draw and drain like a shower. They don't work so well in batch mode. And there is an International Building Performance Simulation Association. They do a lot of work on building simulation. They've been around since, I think their first conference was in the 80s. They have annual international conferences every couple of years. They have an academic journal. Lots and lots of work on it, but they don't pay much attention to domestic water or hot water. Surprisingly little, and I'd like to see us get in on that. And that's it for me. Chris, you can pass it on to other people, or if there's questions, quick questions.
Yeah.
Except I'm probably over my time.
Yeah, I think maybe at this point we save questions for the end. But thank you for that, Jim. That was really great. Yeah, and I'm going to move us along and introduce Carmen Cejudo, who is doing some work now with SRE 90.1, doing some much needed updates to hot water systems for that building standard. So yeah, with that, Carmen, take it away.
Thanks, Chris. Hi, I'm Carmen Cejudo. I'm a mechanical engineer with the Pacific Northwest National Laboratory, Pnnl. So I'm going to talk about ASHRAE and how we are handling the modeling on the 90.1 committee, and talk a little bit more about Pnnl and our work with energy codes and how we advance this topic. So if water is the source of life, hot water is the key to our civilization. I have family in Texas that went through that very terrible cold snap recently, and some of them didn't have water for a period of time. So it's, you know, not great that you don't have potable water, but then also when you don't have hot water to take a shower or for laundry, etc., that can really have a great impact on how you feel as a citizen of this country. So domestic hot water happens to be the second largest end use in buildings, in our homes, as well as some commercial buildings, especially as we're starting to tighten down on envelopes and lighting and HVAC systems, because as Jim addressed, we don't always have the most up-to-date ways to deal with domestic hot water. It's been a slice of the pie that hasn't changed tremendously since the 70s. We are looking to address that with our different modeling tools. Obviously, because climate change is such a threat to our civilization, we really need to start moving the needle, and everything in the buildings has to start being ramped down. So at Pnnl, we are using national codes as a way to target energy use reduction overall. So this is a chart showing how ASHRAE 90.1, from its inception in the mid-70s, has really set that baseline, and using the 90.1 and different jurisdictions that adopt the codes, we're able to start ramping down total building energy use. So you can see there the rates of change and the predictions that we have for future cycles of the standard. A little bit of an overview on Pnnl and our codes program. We are funded by the Department of Energy, and we have 3 major buckets that we support: development of codes, adoption, and compliance. So this presentation, I'm going to focus on the development, because this is where we really start diving into saying what was the previous standard, what measures can we incorporate and roll into future standards that will become industry practices. The adoption, that really does depend on your jurisdiction. We also support that, as well as compliance, meaning training and resources and field studies to understand how the codes are being implemented throughout the country. So for energy savings, looks like that chart does not populate very well. We'll have that in the printed version when you download the slides. But essentially, we have 16 different prototype building models, which I'll show you. And we are using climate zones that are representative of a variety of different climates throughout the country. And actually, these are all ASHRAE standards, so it's not just the US, it's international. But for our work, we focus on the US climates. As I mentioned, we have 16 different prototype building models. So these are standards that we use for all of our modeling. And they range from small office to high-rise apartments. We use Energy Plus, which is an open source all building software that incorporates a lot of different real modeling inputs to bring together the, Jim, I think you advanced on me, to bring together the different measures that we look at. I think we're back to our prototypes here. So as I was mentioning, we use Energy Plus, and there is a feature within it that has hot water modeling as part of it. So the inputs that we include in those prototypes are the types of equipment, whether it's gas or electric. We're also looking into heat pumps and more current versions. Peak use. So Jim had mentioned, it's really up to people. So whether they're in an apartment building or in an office, what are the usage patterns and the peak GPMs that are used at different schedules. Storage volume, if there is a storage tank. Schedules, as I mentioned, depending if it's an office or a hospital that's running 24 hours. Incoming distribution and incoming and distribution water temperatures. So temperatures that there's an algorithm that calculates the groundwater temperature, what we have to heat the water up, and then also the water that goes out to the system. So one of the comments that Jim had made regarding at that endpoint, are you waiting a long time for the hot water? So that is an input that we capture in the models, as well as distribution piping. So some of the prototypes, which I will show you here in a minute, do not have distribution per se. They're really more of a point of use, but some of them do have large distribution systems with recirculation. So that's all included. Energy efficiency measures that we are capturing in the models are improved pipe insulation. We also look to reduce tank losses through additional insulation around the tanks. Looking at efficiency upgrades as industry improves efficiency of electric and gas water, well, maybe not so much electric, but on heat pumps, but gas water heaters as well. Those have been captured in the models. Recirculation and pump energy controls of that loop when we have a loop. And also we are capturing energy efficiency measures with really high capacity equipment, over 1 million BTUs. So that's something newer that we're incorporating. With the whole building energy simulation, you can see here, this is a snapshot from 2004, which is the blue bars, to 2019, the current version of the standard. Here's where we're seeing the various changes for the different prototypes. So saying from that older version of 90.1 to the more current one, incorporating those energy efficiency measures. Granted, this is incorporating all of them. So it's lighting, it's HVAC, it's also the service water heating components. And you can see there we're targeting for this next round about a 37, almost 38% reduction over the 2004 baseline. And for this coming version of the code, you can see here, based on the inputs and the measures that we're incorporating, breakdown based on the prototypes. So the ones that have the highest service water heating component of the total energy use of the building are what you would think that it makes sense. So quick service restaurants, those fast food restaurants, large hotels, small hotels, mid-rise apartments, high-rise. So those are where you're going to see a lot more of the hot water demand being a factor of the overall building total. And with the prototypes, I was actually surprised when I joined the lab in July of last year to learn that the mid-rise multifamily prototype, it's just the way it is. It does not include recirculation. This building model includes hot water tanks within each unit. So that one does not have recirculation. So the ones that are grayed out, you can see, are really more point of use, smaller, either electric or gas water heaters. Where we do have larger buildings with distribution, it depends on the occupancy type of whether we have controls on that recirc pipe or if they are operated 24/7 on the recirc. So all of that energy use is calculated, and here's another snapshot of, it might be a little hard to see, the different prototypes of the service water heating EUI compared to the total for the building. So that's just another summary version of that previous slide that I showed you. So again, quick service is kind of right up there. It's a high EUI overall energy use, and of that, the service water heating is almost 20%, one of the larger categories aside from the high rise. So coming up, we are looking to make the models better and to take the lessons that we've learned as an industry and to improve how we model domestic hot water systems, but more importantly, how we can quantify energy saving measures. So they are broken up into 4 categories of the work that we're doing here to incorporate into the next cycle of ASHRAE 90.1. So we're looking at demand. As Jim was alluding to, there's new methods of how we calculate that peak load. So we're going to be incorporating those and assigning a value to how much energy we could be saving off of that. We're incorporating heat pump water heaters and the technology and the efficiencies that we can gain from this new category, both on the unitary side, meaning the smaller household style heat pump water heaters, as well as the larger distribution systems for central systems. We're also looking at distribution, meaning can we incentivize shorter pipe runs, reduced recirculation losses, et cetera. And then domestic hot water pipe installation. So that can get a little tricky because it's a first cost, but kind of like your envelope, if you invest in it in the initial start and construction of your building, kind of set it and forget it. So might as well make those pipes a little beefier. So we're definitely looking into upgrading the minimums and then also having an additional measure for going above and beyond what minimums are increasing. So I'm coming up at the end of my time here, and so more research needed. We're always trying to improve, especially with the service water heating sector, how we incorporate the measures into our models. So we need to continue doing more updates on demand as we start seeing more real-life research. Hot water temperature maintenance is a big deal, at least for me. How can we help impact design in the industry by either really reducing the amount of the recirc loop or having alternatives like heat trace or some of the other new products that are coming on the market. Reducing pipe lengths and also addressing operation and controls in regards to Legionella and health and safety concerns. And then, like I said, pipe installation, we're ramping that up, and we're going to also look at enforcement of how we can make sure that whatever we spec and is required in the codes is actually installed in the field. So with that, thank you, and I look forward to the Q&A section.
Great. Well, thanks so much, Carmen. And yeah, don't forget, put your Q&A questions down at in the Q&A box down at the bottom, and we'll get to them at the end. So yeah, I really appreciate that, Carmen. We're going to move on to our final presentation here. Again, Miriam Blocker, she's from KWR Water Research Institute. She will be talking about their Simdium model, which is a simulation of water demand and use model for domestic hot water systems. So turn it over to you, Miriam.
Thank you so much. Yeah, so KWR, just a short introduction for people who don't know. It's the Research Institute for the Drinking Water Utilities in the Netherlands and Belgium. And I started there more than 15 years ago, and I made the model for them, but it was also for the installation sector that they were also involved. So that's why we, from the start, included the hot water demand, not just the drinking water demand. So this slide sums up a little bit how the model works, how Simdium works. And actually, Jim Lutz gave a terrific introduction to what such a model should look like. I guess I followed the same line of thinking when I started making this. So in the heart is the building, in this case, a house with appliances and also with people. If you look really carefully, you see a person there in the kitchen. The information that is required as an input to the model is all based on physical meaning of the parameters. So for example, how often do people flush a toilet? So not how often is a toilet flushed, but no, how often do people flush a toilet? So it's really the people that do this, that have this behavior. Other information is how long do they take a shower, and information on their behavior. For example, when do they leave the house? When do they return home? When do they go to bed? When do they get out of bed? And those seem to be very much related to when people are more likely to use water. It's a stochastic model, as the process itself is also stochastic. And in this case, it means we do not have an input parameter that's a single value, like the number of toilet flushes per person is 6, but it's actually a probability distribution, in this case, a Poisson distribution. So with a random number generator, you can then get in a specific model run, a specific value for the number of toilet flushes or for how long people take a shower, for example. It's a small spatial scale. It's at the tap, at each tap, and not even that. It's also, is it cold water use or hot water use? It's a small temporal scale, and we start with 1 second. You can, of course, aggregate after that, but it is in its space a very small temporal scale. And it leads to realistic demand patterns. So in this, I hid a little bit the legend of that, but the colored lines, the red and the purple, are measured. And this is the demand of a street of about 140 homes. And in black, you can see the model results. And actually, if I hadn't told you which is the model and which are the measurements, you would not be able to tell which is which. And they do follow quite the same pattern over the day. When they go down at night, how high it is during the night, then the morning peak coincides very nicely between measurements and model results. And then the afternoon, during noontime, you see a little peak again, it goes down, and then people start coming home and making dinner. And also the variation between one moment and 5 minutes later, in this case, is quite similar for both measurements and simulation results. So with that, we can go a step further to model not just the demands, but also to model the premise plumbing system. So this is a graph here showing in the middle a little bit of what an EPA net hydraulic network model would look like. On the bottom, you see the water meter. That's where the water would come in from the drinking water utilities, and it goes up to a toilet and the kitchen, to the first floor where there's another bathroom, another floor up where there is the washing machine, and in the Netherlands, typically the hot water boiler is in the attic, and then pipes going down again to serve the hot water to kitchen tap and shower and so on. And then each tap gets its own unique demand pattern. So the shower has a pattern, the kitchen tap, and you can see the black and red are the differences between hot and cold water. And then with this combination of demand patterns and your hydraulic network model, you can calculate hydraulics, so that's pressure and flows, the water age that Jim already introduced, so how long is that water inside the system, and then water quality. And this could be anything as long as you know how to model it. And I'll give an example of temperature modeling. So what would that then look like? For example, if we model this same house with the same layout that I just showed, you can have demands. And I didn't go as short as 1 second, but I did 10-second time steps. And you can see the demands in blue. And in red, you can see the water age in the pipe just before that kitchen tap. So when there is a long stagnant time, you can see water age going up. And the lower figure shows the same thing, but for the hot water side of the kitchen tap. So that's typically used a lot less often, especially if people have a dishwasher installed. And you can see that water age could be quite high. It can be up to 70 hours almost. So there's quite some stagnancy possible with, well, potential Legionella and other things. We've made a temperature model also related to hydraulics and basic physics of heat exchange between water and surrounding air. And this model was also tested in Technical University of Delft. They built the same system that I've been showing so far. They put it in an empty elevator shaft a few stories up. They applied the stochastic demand patterns that we modeled. So we have a perfect match, or almost perfect match, between model and the real system. And then this ran for 365 days with 365 unique days of demands. They were all different. And then the temperature was modeled as well. And then you can see in the lower right that the temperature, the results for the model and what was measured. And there were some unexplained results, but generally they look very, very similar, and the model was validated this way. And there were some other measurements also done, like microbial qualities, and that's a different model. I'm not discussing that today. So we also modeled the temperature, and the results are shown here. The lower graph is just a zoom in of the first few minutes of your shower. So in blue, again, the demand, in this case, just the hot water side. And there is, of course, at the same time, some cold water demand, because you don't want to get a shower under 50 degrees Celsius, but maybe more like 38 or 40. So some cold water is also introduced there. You can see that this particular person took a shower for around 9 minutes, or probably for 1.5 minutes less, because that's, in this case, how long it takes for the hot water to arrive. So probably the first 1.5 minutes, they will not be taking that shower, but waiting for the hot water to arrive. And then you can see the same as what Jim showed in his measurement, that there is this decay where the temperature again drops to room temperature. What we did after we have done the validation of the demand model for both hot and cold water, where we did the validation of the temperature model, we could also determine final energy that is needed to produce hot water, and also some other stuff like, okay, what does that mean in terms of cost and CO2 footprint? So the basic modeling setup is we have the demand model, then we add some hydraulic modeling with temperature modeling and some post-processing to determine costs. And we did that for a few different standard households or houses, I have to say first. So a really simple one just has a kitchen and a bathroom faucet and a shower, but not a lot of extra. And the more luxury one would have also a bath and a second shower, for example. So there were various dwellings that we did. And then we put different people inside those houses. So in this case, you could think of a two-person household with no children, or a family with grown-up or teenagers, so older children, and they have different behavior, they have different results. Then to determine the final energy, we also need to take into account losses. For example, the heating of the pipe, heat loss during transport, and also cooling down of the hot water that is still in the pipe during that stagnant period. And there's also losses in the heater itself because it needs to keep its temperature at a certain value. Some background information on what the plumbing looks like, and this we tried our best to put some SI units as we have, so in meters and millimeters, but also for you to see some feet and inches, and then the bottom table shows volumes in liters and gallons. So basically that more luxury type has a few larger pipe diameters, so also the volume inside the pipes is larger. And then the next step is to determine the total energy needed, and if this was used, is this gas, is this electricity, is it green electricity or not, and that will determine cost and CO2 footprint. So some results here, quite a busy graph. The figures or the colors here indicate what it is. The first number is the temperature of the cold water as it comes in from the drinking water system. So that is around 10 degrees in winter, the bluish bars, and 20 degrees in summer, the green, orange, yellow ones. On the left, the two-person household without children, and on the right, the family with teenagers in the same building, I have to say. And then this WTW is a Dutch abbreviation for the shower heat recovery. And you can see that the bars are the average and the lines around it show the 10th to 90th percentile. So here we can see that between having a shower heat recovery or not, it's slightly more efficient to overall for your heater to have one. The differences between two-person household and family with teenagers is obvious. Of course, there's twice as many people, but the energy use is not twice as high exactly. There's some efficiency in there. There's a difference, of course, between winter and summer, where in summer you need less energy to get your water to around the same temperatures. The error bars are quite large. So it could happen that a family that is more or less the same, but behaves a little bit differently in one house, and their neighbors in the house next door, one of them has a shower heat recovery and the other one doesn't, that the one that doesn't have it can still be using less energy. That's basically what those error bars indicate, because people behave a little bit differently. They take shorter showers maybe, or more one after another, so there's less heat losses. So the final slide, you can use this model for various more things, and Jim also indicated a few that he would like to see, and some of them we did. So we did model temperatures at taps, and you can see the effect on waiting times, and you can therefore look at a more optimal design for your system. And we can also apply this in larger buildings that have heat recirculation systems, but we haven't done that yet. And then you can look at energy requirements, and that also will help you to have a more optimal design. And we have model temperature, and the next challenge for us is to also model microbial water quality and see what the effect of that would be. Thank you so much, and also quite looking forward to the chat.
Great. Well, thank you so much, Miriam. We have about 8 minutes here, and so if all the presenters would please turn on their cameras and get ready. We have some questions lined up. I wrote down some questions, but we've got a lot coming in, and if you have more, please send them. I'm going to start here. Actually, Miriam, since you were just going, we'll keep going with the question for you. So Pete Skinner from E2G Solar says, excellent work. Love to come to Holland to see your system sometime. Have you applied this capability to multifamily buildings?
Not yet. Well, no. Well, we have to to the demand part, but not to the hydraulic and temperature part. Not yet. So that would be nice. Well,
at some point. Okay, and so then next question. So Gary Klein from Gary Klein Associates asked Carmen, so how does the 90.1 model treat the pipes that branch off the circulation loops? And he also asks, in all prototypes, how does it treat the events that are too short to reach the fixtures as hot water?
Thanks, Gary. That level of granularity is not very well captured in the current modeling. There's some limitations regarding Energy Plus that have that impact, as well as just how we would document that for different prototypes. So at this point, not great, I would say. That's certainly one of the measures that we want to look into in future cycles.
And this next question is from Matt Malinowski from CLASP. I think this might be directed at Carmen, but I think it really could be for any of you. So how well do models work across countries? And would you have any resources with data that would allow international modeling?
I'll take this first. So ASHRAE 90.1 is a standard that can be applied internationally, and often it is. The main difference would be your climate zone, right? So the weather file that is used to run the simulations would obviously change depending on your international country that you're looking into. the peak demand, I think, is where we would want to look at your inputs for whatever your different country is. We're really focused on the United States, so those peaks are based on ASHRAE and IAPMO and ASPE research. So it's just a modeling tool. It would really just depend on the inputs and the weather file.
Yeah, I can also say something about the international. For us, it's quite a challenge. A lot of differences in how systems are designed. So pipe diameters tend to be larger, longer in the US than in Europe. And behavior is also a little bit different, both with respect to how often you would use certain appliances, but also how people work from home or not, or leave the house earlier or later. So coincidence of demand and peak demand is influenced by that. But for the US, it seems that we have quite a lot of potential input data to run the model, and I have worked with some people in the US to look at that. And so I think the model Simdium works quite well there as well. Yeah.
Great.
Mary?
And Jim, yeah, any thoughts?
Yeah, I wanted to press Miriam. I've heard that Simdium is there's work to make it open source, and that you might be able to share it at some time. And related to that question, on one of your slides, you say you use EPA Net and Simdium. So on the open source question first, and then the other one, what is the difference between Simdium and EPA Net?
All right. So the open source, yes, I built it originally in MATLAB, but we're converting to Python. And then we want to make it open source and invite people to use it, but also maybe add onto it. It shouldn't be long, but I've been saying that for a while. I'm not doing the translation myself, my colleague is, but I think within a few months at least, before the summer, I can say. And then the differences, so Simdium is really the model that produces demand patterns. So that could be just text files you could put in Excel or something. It just produces that. EPA Net does the hydraulic modeling. So depending on pipe lengths, pipe diameters, pipe wall roughness, and the demands, and also the pressure that is available, it will show you how the water flows through the system, at what speed, what is the pressure that you still have left at your shower, etc.
And that one's from the US EPA, actually.
It is, yes, it is. And that is also open source. Everyone can use that.
Okay.
Great. So I think we have probably time for one more, and then we'll go over to the Zoom session. So if your question doesn't get addressed, because we've had quite a few roll in here, just ask it during our Zoom session. So here's a conceptual one for Jim. So Gary asked, do you have a sense of the percentage of hot water events that do not actually reach fixtures? And should this be even considered hot water?
I want to hear Gary's thoughts on that. I'm guessing that, well, obviously no one's going to take a shower in cold water, so everybody waits for hot water to arrive for their shower. For faucet events, if the draws are clustered, meaning you use the sink and then 5 minutes later you use it again, those ones will get up to hot water. Or if it's on a trunk and it's a couple branches off the same part of the trunk, then the hot water will eventually get there. One of the projects I did with Gary, we were seeing maybe about 20% of the water that was delivered was not hot, was not above the hot temperature. So I don't remember looking at it in and this was a research study limited to, I think, only just one draw pattern and various plumbing configurations, but it's not, that wasn't the number of draws, that was the amount of hot water. So, it's you got to separate the amount of hot water from the number of draws, because obviously no one's going to shower. Well, it might happen a few times. People do strange things. If you ever look at field data, you'll find out. But most people like their showers hot.
Whereas I think this was the difference between water demand, hot water demand, and hot water use. Yes.
And then taps for washing your hands or rinsing off, rinsing out a glass or something. You may not even wait for hot water. You may not even wanted hot water. You just wanted water that wasn't, really cold. And so that might have been acceptable. It's certainly what you can see in what limited data we have at the taps. So.
Great. Well, thanks. Well, let's continue talking about this. Let's transition now to the Zoom. We're a couple minutes over. So see everybody in the Zoom chat room.